Have you ever just stood there, looked up at a passenger jet flying overhead, and thought to yourself, how in the world do we even build something that complex? I mean, it's not just a machine, it's basically a city in the sky. And the secret to pulling it off? Well, it isn't just about powerful engines or slick aerodynamics. It's really about a philosophy for how you put the whole thing together.
I mean, just look at this. This picture says it all, right? A modern jet has millions of individual parts, and they all have to work together perfectly. You've got your electrical systems, hydraulics, avionics, life support, engines. The list goes on and on. It is literally a system of systems. And in a machine like this, one tiny little failure could cascade into a total disaster.
So that's the million-dollar question, isn't it? How do you possibly tame that kind of complexity? How do you make sure every single part does its job every single time when there is absolutely zero room for error? Well, it turns out there's a formal, really rigorous process for doing exactly that.
And that process is called systems engineering. Now, this isn't just some corporate buzzword. It's a whole discipline. And the key idea is right there in the definition. You have to understand the entire problem from the very, very beginning. You figure out what the customer actually needs and what the system has to do long before you even start thinking about how you're going to build it. It's like a blueprint for thinking.
You know, the source material for this explainer puts it beautifully. An aircraft isn't just a bunch of parts bolted together. It is one unified system. The landing gear can't say to the navigation system, hey, I don't need you. Every single piece is connected. If one subsystem fails, the whole aircraft is at risk. And that idea, that's the absolute core of this whole philosophy.
All right, so that's the big idea, but how does it actually work in the real world? Let's get into the first stage, how you take a big, high-level mission and break it down into concrete nuts and bolts engineering requirements.
This quote from Robert Persing just hits the nail on the head for this first step. You have to learn to separate the what from the how. A motorcycle has components, right? The engine, the wheels, the frame, that's the how. But it also has functions to accelerate, to turn, to stop. That's the what. And in systems engineering, you always start with the functions.
This whole process is called functional analysis. You sit down and you systematically map out every single thing the aircraft must be able to do. So, why start here? Well, think about it. If you don't get the what right, then everything you build, the how, is going to be flawed from the very beginning. This analysis becomes the bedrock, the foundation for every single decision that comes after it. And here's how those functions become real engineering targets. It's a process engineers call flowdown. You start at the top with a simple market need. We need to carry 250 people. That flows down and becomes a specific requirement for the aircraft. It needs a range of 7,000 nautical miles. Then, that flows down again to become a very specific requirement for a subsystem, like the engines needing exactly 11,000 pounds of thrust. It's this beautiful waterfall of logic.
Okay, so you've done your homework. You've got this massive, detailed list of requirements. You know what the plane needs to do, down to the smallest detail. Now comes the fun part, the creative part, actually designing the thing.
In the world of systems engineering, they call this synthesis. And it's that magic moment where you take all of that abstract analysis, all those requirements on paper, and you turn them into an actual physical design concept. But this isn't just about sketching a cool-looking plane. It is a massive, incredibly complex balancing act.
And the heart and soul of synthesis is the art of the trade-off. See, every single engineering decision is a compromise. You want to carry more passengers? Okay, but that adds weight, which means you can carry less fuel, which kills your range. You want to use those fancy new lightweight materials to fix that? You can, but your cost is going to go through the roof. The job of an engineer isn't to find the perfect solution. It's to find the optimal compromise between all these competing demands.
And hey, for those of you studying digitalization, this is exactly where this stuff gets real for you. This whole process isn't just for bending metal. A top-level requirement, something like the plane must respond to the pilot's controls within X milliseconds, flows directly down into the digital world. It becomes a hard, non-negotiable requirement for the processing speed of the flight control computer or the data latency on its network. The physical and the digital are totally intertwined.
So we have a design. It's built on a solid foundation of requirements and clever trade-offs. But how do we know it's actually safe? This brings us to what is, without a doubt, the most critical phase of all, assurance.
And let me be clear, this is not just some academic exercise. This process has profound life-or-death consequences. The incredibly rigorous, painstaking application of systems engineering is a huge reason why flying has become the safest way to travel long distances in the history of humanity. The numbers don't lie.
This incredible safety record is built on a defense that has multiple layers. First, you've got regulators like the FAA who set the rules of the game. Then, you have these analytical tools like the functional hazard assessment, which is basically a pre-mortem. You look at every single function and ask, okay, what happens if this breaks? And then, even before you build anything, the preliminary system safety assessment looks at the blueprint itself to catch potential flaws before they ever get off the drawing board.
But here's a really important idea. Modern engineering goes beyond just preventing failure. You have to understand the difference between safety and resilience. Safety is about making sure the engines don't fail in the first place. Resilience, on the other hand, is about accepting that someday something totally unexpected will happen and designing the rest of the plane so it can still fly and land safely even if both engines do fail. That's your miracle on the Hudson. That's resilience.
So as we start to wrap this up, you can see that systems engineering isn't just a checklist of steps. It's a really powerful way of thinking that you can apply to pretty much any complex problem. It's all about adopting a certain kind of mindset.
First up is the systems mindset. This is all about zooming out. It's that ability to see the whole forest, not just the individual trees. It's understanding that the little component you're working on isn't an island. It's one note in a much, much larger symphony.
Second, you need the risk mindset. This basically means you have to become a professional pessimist. You have to have the discipline to constantly ask, how can this break? What could go wrong here? Where are the weak spots? You're actively hunting for problems so you can solve them before they ever happen.
And finally, there's the resilience mindset. This is the really forward-thinking part. It's about building systems that are tough enough to survive things you didn't even plan for. It means you're not just designing for everything to work perfectly. You're designing for a graceful recovery when things inevitably go wrong.
So this framework, this combination of process and mindset, this is how engineers pull off the monumental feat of building a city in the sky. It's how they take what seems like overwhelming complexity and turn it into something predictable, safe, and reliable. So that just leaves one question. What complex system are you going to build?